So in the case of problem number one, hopefully you just realize that the one on the left is in parallel, the one on the right is in series, and that simply has to do not with the fact that they're actually parallel to one another, because you'll notice in both cases they appear to be parallel. Series just means if I go through one, I must go through the others as well, whereas true parallel means after I go through one, I can find my way back to the battery. I don't necessarily need to go through one of the other two. We take a look at number two. We have a variety of instruments here. The main goal being that on the leftward diagram, the two that are in series are the ammeter and the resistor. Once I go through the ammeter, I must go through the resistor. The bulb and the speaker are wired in parallel because there I have a choice as to which one I want to go through. And in the diagram on the right, the speaker and the ammeter are in series, and the bulb and the resistor are in parallel. For the same reasoning, I get to choose here. I'm forced to go through these two over here. If we want to compare series and parallel circuits, this is where things get a little bit trickier. For a series circuit, it's just one loop. And for a parallel circuit, it could be two or more, so you get choices. If one light bulb goes out in a series circuit, since there's only a single pathway, that single pathway is now blocked and nothing will work, so everything will go out. In a parallel circuit, much like up here, if this bulb goes out, there is still this pathway to get through this resistor. Therefore, removing this bulb will not affect anything. Technically, if I remove both, it would shut everything down because then there'd be no complete circuit. But if I just remove any one in a parallel arrangement, the other one is unaffected because there is still a pathway. This tends to throw people off the most. As the number of resistors is increased, the overall current in a series circuit decreases. If I'm throwing resistors in a series orientation, every electron will have to go through every single resistor that I throw down. So if we want to take a look at an example, this would be perfect. Here I have three resistors and one choice. I have three resistors I have to go through because I'm only given that one choice. Over here, while I still have three objects, or like three resistors, I have the choice to go through any one. So while here I have one choice and I have to go through three, here I have three choices and I only have to go through one. So it's kind of like being forced to do something versus you get the choice and you also have to do less of it. So in that case, when I add resistors in series, it decreases the current because there's more resistance, there's more stuff in my way. In parallel, I'm not really adding resistors. I mean, physically I am, but I'm not adding them in the way of the electron. I'm actually adding options. Any one electron now is not forced to go through three. It gets its choice of which of these three it would like to go through. When you give these electrons, when you give people choices, it decreases the resistance. With more choice, there is more that you can do to make sure you get through easier. And this just goes hand in hand. If the current is decreasing, that's because the resistance is increasing. I'm throwing more things in the singular pathway. And for a parallel, the current is increasing because I'm actually decreasing the resistance. Now I'm saying instead of having to wait in line, I'm giving you choices. If this is blocked up, travel here. If this is blocked up, travel here. When you get more choices, your resistance goes down, your current goes up. For number four, when we're looking at these what we call voltage drops, we just have to remember I leave the negative terminal of the battery with my full voltage, in this case 120, I must get back with 0. If I'm told that I'm giving up 80 here and there's only two resistors, the voltage drops across both must add up to the total 120. That means this would have to be 40. So I leave with 120, subtract 40, so I technically now have 80 here, spend my last 80 and get back with 0. Same logic applies in diagram B. Leave with 12, I lose 3. I know I'm going to lose 4. So if I start with 12 and I know I have to spend 7 here, well, on the remaining resistor, I'm going to have to spend 5. So it totals up to the 12 that I lose from going to the negative to the positive terminal. For number 5, there's two ways we can look at this. I do want to be clear. A conventional current suggests that the current leaves the positive and travels to the negative. We, in this class, are going to look at what actually happens, and we're going to look at the flow of electrons from the negative terminal to the positive. So in this case, we will assume that whatever the voltage here happens to be, at G and F, I will have the full voltage because I have not gone through a resistor. If this is a 100-volt battery, that means that I will have 100 volts at G and F because I haven't spent any going through a resistor. Without more information, I don't know how much I will lose, but I will lose and spend some voltage. There'll be a voltage drop as I go from F to D because I'm going through a resistor. From D along this wire, whatever that lower voltage value is, because I spent some here, will be constant. I will then drop again as I go through the light bulb, pass through C, and then as I go through this light bulb, I will spend the remaining. So at A and B, I technically will have 0 volts because I don't have any resistors to go through. So looking at it this way, G and F will be equal. I've spent nothing. D will be slightly less, but D will be more than the others because D comes before we spend voltage at this second resistor. After traveling through the second resistor, C is a little bit less than D, but it's still more than B and A. And when I finally spend my remaining voltage, B and A will be 0. Therefore, if I look at this, A, the voltage at A will be much less than at G. At G, it's the full voltage. At A, it's 0. I've gone through 3 resistors to get to A and spent all my voltage. So A will certainly be less because it's 0 versus the full voltage. B is also 0, and since C comes before the final resistor, I still have some voltage left to spend. I will spend it all to get to point B and travel through this light bulb. So B, which is 0, will be less than C. B will also be less than F, because F, much like A and G, F is all the way at the beginning. I have full voltage. After going through 3 and spending it all, B will have 0. Now this last case here, which is I, that is the current. I is the unit of current. There is only one pathway, so while different amounts of voltage will be spent at different resistors, the number of electrons and the current which leaves the negative terminal must go through this section, this section, this section, and this section. There is nowhere else for it to go. Therefore, at any single point, you will see the same current. If you stood at point G and you watched 7 electrons travel past G, and we let them go through the circuit, and I was standing at A, I would see those same 7 electrons because there's nowhere else for them to go. Similarly, over here, they've flipped the negative and the positive terminals, but A and B will have the full voltage. C will have a fairly significant amount less because it's gone through 2 resistors. D and F will have 0 because at this point I've traveled through all 3. A has the most. It is certainly greater than F. F is 0. A is the full voltage. B is greater than C. Again, the full voltage is at B. C, I would have spent at whatever amount I spent getting through these 2 resistors, so C must be less. D and F, this is at the tail end of the circuit. There are no more resistors to go through, so D and F will both have 0 volts. In the case of current, it's a series circuit, so the current is the same everywhere. For number 5, when it comes to figuring out the total resistance, it's quite simple. I add them up. Since I have to go through every resistor, I will just add them up directly. If I have 2 4-ohm resistors, that means I have 8 ohms, or an equivalent of 8 ohms. If I had 3 of those 4-ohm resistors, it would be the same as having 112. 4 4-ohm resistors, the same as 116. For number 6, I have 3 light bulbs connected in series. That immediately tells me I have one pathway. The filament, which is the part of the light bulb inside the glass casing that lights up, one of those burns out. That means that electricity can no longer travel through the bulb. The remaining 2 light bulbs will still be lit. Well, that is false because once you break that pathway in a series circuit, you have broken the only pathway there is. Every bulb will go out. There will be no current. There's no officially closed pathway from the negative to the positive terminal. In each of these cases, 7, 8, and just 7 and 8, I've basically given the math down below. I find the total resistance, since it's a series, by just adding them up, 2, 4, 6, and then I use Ohm's law. The voltage is 12, the current is unknown, and the total resistance that we found is 6. Therefore, we should be able to calculate the current that's present that leaves the negative terminal and arrives at the positive terminal. Likewise, I've done the same setup for the diagram on the right, shown the work below. The total resistance I find by adding up the 6, the 4, and the 2, and then I simply use Ohm's law and the given voltage to figure out how much current will travel through this circuit. In number 8, it's the same setup. However, the variable that I am missing is different. In these cases, it was both current. Now, in this case, we don't know the current here. So again, this is similar, but then we look for the the resistance here. We look for the voltage here. So it's the same setup. They're just asking us for a variety of different variables. Same thing here. I know the total resistance, 30 and 30 gives me 60. I know the voltage is 120, so I use Ohm's law. 120 equals the current times 60. I must have 2 amps of current. All right, I've shown the work for the rest of this down below. I'm not going to go through step by step. Although, I will do the second diagram because it is asking for the resistance. So I don't know the total resistance because it would be 2 plus 4 plus whatever this happens to be, and I don't initially know that. I do, however, know the voltage and the current, so I use Ohm's law to figure out that the total resistance must be 12. Since I already have one 4 ohm resistor here and one 6 ohm, I will take those away. 6 ohms is the only value that will give me a total of 12 ohms when I add these together. You'll have to use the same method to solve the diagram down here. This one is a little bit more straightforward. But take a look through and make sure you understand how to use Ohm's law as well as why I was subtracting out resistors here, because this gives me the total resistance and I'm looking for one specific. For the case of number 9, it's hopefully straightforward. Same voltage, one resistor of 2 ohms, 2 resistors of 2 ohms each. Since this is series, the total resistance here will be 4. If I apply the same voltage to a higher resistance, I'll get less current. There's more stuff in the way, so the resistance of X will be lower because there's 2 versus 4, and as a result, the current out of the battery in X will be higher because there's less stuff in the way. The battery can push that current through more quickly. Or number 10, we have 3 identical light bulbs. Only some of these things can be true, so let's look at each one. I'd like to make the current measured at X increase. Well, this is a series circuit, so the only thing that can happen is current can only travel in one direction or one pathway. It would technically travel this way from the negative to the positive. Since this is a series, X, Y, Z, W, whatever the current is at W will be the same at Z, Y, and X. If we would like to increase the current at any point, end of the day, we must decrease the resistance or use a bigger battery. A bigger battery will push more electrons out at a higher speed, and less resistance will allow the same battery to push more out because there's less stuff in the way. If we look through these, that's what I've basically answered here. I can decrease the resistance of 2 of the bulbs. Decreasing the resistance of any of the bulbs will lower the resistance of the total circuit, or I could increase the voltage of the battery. Either one of those things will cause the current to go up. Remove some of the things obstructing the flow, or provide a larger voltage source, a larger battery, so it can provide a much bigger burst of electrons as they travel from the more negative to the more positive terminals of that battery. Or number 11, 3 identical batteries, much like the previous problem. This one can seem a little tricky at first. First thing to realize, potential difference is just voltage. So what they're saying here in case A, the voltage between X and Y is greater than the voltage between Y and Z. And what they really mean is the voltage spent. So an easy way to evaluate this expression, to go from X to Y, I go through one resistor. So I spend the voltage I would spend on one resistor. Between Y and Z, I go through one resistor. I will spend the same voltage from X to Y that I will from Y to Z, because you're told that these light bulbs are identical, so I'm going to be spending the same amount of voltage if I go through only one. In case B, the difference between X and Y, which is going through one resistor, is greater than between Y and W. Actually, Y and W will be greater because I will spend twice the voltage because I'm going through 2, so this is also false. The third one, the voltage spent between Y and Z, which is going through one light bulb, is greater than between Y and W. That again is false. Y and W will be twice the voltage spent between Y and Z because you go through a second bulb. I can continue with each of these. However, the correct answer is D. The difference between X and Z, which is going through 2 bulbs, is greater than between Z and W. I'm only spending voltage through one bulb, so it will cost me more voltage to get through 2 bulbs than it will to get through 1. Number 12, 3 identical light bulbs are connected. Which of the following statements is true? Well, the current will be the same everywhere, and therefore those bulbs will have the same brightness. There's only one pathway for current to travel through. You cannot, absolutely not, get different brightnesses in the bulbs, assuming they are all identical. So none of these would be correct because they all have the same current. If you'd like to increase the brightness of the bulb, increase the current. If you'd like to decrease the brightness, decrease the current.